Hello and welcome back. So today we will have the last class for the chapter of matrices. So let us start our class with some examples on inverts of a matrix. So here is a question. Find A inverse if A is given as this matrix 2 1 1 1. Okay, so this is your question. You are required to find A inverse if A is equal to this using row operations. So using row operations, try to find the inverse of this matrix. Okay, this is your question. So let's try to solve this question. So we have the matrix A is equal to 2 1 1 1. Now recall, in our previous class we have discussed what is the first step. The first step is to write this equation A is equal to I into A. If you are using row operations, for column operations you would write A is equal to A into I. So since you are using row operations, you will use this equation. So now after writing this equation, you put the value of A in this position. So putting the value of A, we have 2 1 1 1 equal to, put the value of I here. I is 1 0 0 1 multiplied by A. A you put as it is given. So now after putting this value, we are left with this matrix equation. Now what is our aim here? Our aim is that we have to make this left hand side of this matrix equation equal to identity matrix, just like this, by using row operations. So using row operations, try to make the left hand side equal to this matrix. Okay, so what should we do first? That means we should achieve this matrix here. We should aim at achieving this matrix. So let us try to make this element 0 in this position. What can we do so that this 1 changes to 0? Think about it. What can we do in this position? Can we divide the first row by half, then subtract the second row from the first row after halving the first row? Will it give it a 0 here? Let's check it out. If we do this operation, if we change the second row to second row minus first row divided by 2. Second row minus first row divided by 2. So take a look at the second row here. First row is 2 1 and the second row is 1 1. Now here we have to divide the first row by 2. So dividing the first row by 2, we have 2 by 2 and 1 by 2. Okay, 2 by 2 is nothing but 1. 2 by 2 is 1. Okay, now R2 minus R1 by 2. So R2 minus R1 by 2 is 1 minus 1 is 0. So you have to put the value in the second row. So here it is the second row. So first row remains the same since we are changing only the second row. First row will remain the same as 2 1. And in the second row we will have R2 minus R1 by 2 as we have said here. So R2 minus R1 by 2 is 1 minus 1 is 0. And then 1 minus half is half. Right. And on the right hand side we will have same operation. The first row is 1 0. Look, the first row is 1 0 and the second row is 0 1. Second row is 0 1. So after doing this operation R1 by 2, you will have 1 by 2 and 0 by 2 is 0. Now see here, the first row is not changing, so we will write the first row as it is, and in the second row, that means in the second row we will use R2 minus R1 by 2 just like we have done it here. Same thing we will do here. 0 minus half is minus half, and in this position 1 minus 0 is 1 into A. So after doing this operation, we are seeing that we are achieving a 0 successfully at this position. Now it is 0, it is also 0. What is the next number that we should target? In the same row we see that this is 1 but this is half. So what can we do so that this becomes a 1 here instead of half? So we have to multiply the second row by 2 If we multiply the second row by 2, then 0 into 2 becomes 0, half into 2 becomes 1. So we are achieving a 1 at this position if we do this operation. So now we should do this operation here. That means R2 is getting changed to 2 times R2. So if we change the second row to 2 times the second row, then we will achieve, see, first row remains the same, so 2 1 will not change. However, in the second row, 0 into 2 is 0, and half into 2 is equal to 1. Similar thing we have to do here. First row is not changing, and in the second row, minus half into 2 is equal to minus 1, and 1 into 2 is equal to 2, and keep A as it is. Okay, so now we are seeing that we have successfully attained 1 here and 0 there. Now take a look at this above row, the first row. We are seeing that we must achieve a 0 at this position. We must achieve a 0 at this position. So what can we do so that this thing becomes a 0? Think about it. Can we achieve 0 by subtracting this row from that row and putting the result here? We have to subtract this row from that row, and whatever result we get, we put in this first row. So let us do this operation by changing the first row to first row minus second row. So if we write the same thing here, then take a look at the first row. The first row is 2 1, second row is 0 1. Now in the second row is not getting changed, so write the second row as it is, 0 1, and the first row we have 2 1. So first row will change to R1 minus R2. What is R1 minus R2? 2 minus 0 is equal to 2. You have to put it here. And what is 1 minus 1? It is 0. Similar thing you have to do on the right hand side as well. R1 is equal to 1 0, and R2 is minus 1 2. Now do the same position, same operation. R2 does not change, so write R2 as it is, and in the first row it is R1 minus R2. So 1 minus minus 1 is 1 plus 1, and that is equal to 2. So place 2 here. And what about this? 0 minus 2 is equal to minus 2. Then you have A. Okay, so now we are seeing that we are successfully attaining a 0 here. The last number that is remaining is this number. We have to change this number to 1. So how can we change this number to 1? Think about it. If we divide this entire row with the number 2, if we divide the entire row with 2, then this will become 1. So in the next step, we should do this operation. In the next step, let us say R1 will change to R1 divided by 2. If we do this, that simply means that R2 does not change, so we have to write the second row as it is. Second row is as it is, and in the first row it is getting divided by 2. So 2 divided by 2 is 1, and 0 divided by 2 is 0. And on the right hand side, second row does not change. First row is getting divided by 2. So after division, 2 by 2 is equal to 1, and minus 2 divided by 2 is equal to minus 1. So now we are seeing that this matrix has become identity matrix is equal to I. And we know from our theory of inverts of a matrix, if any two square matrices get multiplied and the product is equal to identity matrix, then these two matrices must be inverts of each other. That means inverse of A is this matrix and inverse of this matrix is A. So we are seeing that if this is A, then this must be A inverse. In other words, we say that we have successfully found the value of A inverse, and that is 1 minus 1 minus 1 2. This is your answer. Okay, so using row operations, we have successfully found the value of A inverse. Let us try another example. Watch this video again and again and try to practice as many examples as possible, because this is quite complex and very easy to get lost. Okay, now let us have another matrix. A is equal to For example, 2174. This is another matrix, and you have to find the inverts of this matrix. Try to find the inverts of this matrix using row operations. So we already know for row operation, the first equation that we should write is A is equal to I into A, right? Putting the value of A, we have 2174 is equal to, putting the value of I into A. Okay, our aim is to achieve an identity matrix on the left hand side. That means we should achieve this matrix. We should try to achieve this matrix at this position. So the first element that we should aim at making 0 is this one. So we have to change 7 to 0. What can we do so that it becomes a 0? Think about it. If we multiply the first row with 7 by 2 and then subtract this row from that row, then it will become a 0. So let us say second row is getting changed to second row minus the first row multiplied by 7 by 2. Try to do this. So if we write first row, then first row is 2 1. First row is 2 1 and the second row is 7 4. Now multiplying the first row with 7 by 2, this will become 7 by 2 multiplied. 2 and 2 cancel out, so we are left with only 7 here, and we are left with 1 into 7 by 2 is 7 by 2. So now we see that the first row is remaining the same, so let us keep the first row as it is, 2 1. First row is not getting changed, only the second row gets changed, and the second row becomes R2 minus 7 by 2 R1. So 7 minus 7 is 0, put it here, and then 4 minus 7 by 2 gets in this position. So what is 4 minus 7 by 2? If you take LCM, it becomes 1 by 7. If you take LCM and then simplify it, it becomes 1 by 7. So you have to put the value here, 1 by 7. Okay, this is equal to the same operation you have to do in the right hand side as well. So write the first row for the right hand side matrix. We have first row is equal to 1 0 and the second row is 0 1. Okay, now first row multiplied by 7 by 2, this is equal to 1 into 7 by 2 and 0 into 7 by 2. So 1 into 7 by 2 is equal to 7 by 2 and 0 into 7 by 2 is 0. Okay, now the first row remains the same because we are changing only the second row. So first row we should write as it is, and look at the second row. Second row now becomes R2 minus R1 into 7 by 2. So R2 minus 7 by 2 R1. So 0 minus 7 by 2 is minus 7 by 2, and 1 minus 0 is equal to 1. Okay, so now we have successfully attained a 0 at this position. The next number that we should try to make is 1. So we have to make 1 by 7 equal to 1. So how can we do that? We have to multiply the entire second row with the number 7. So the next operation that we perform here, is this one. R2 gets changed to 7 times R2. So if you multiply the entire second row with the number 7, then what happens? R1 remains the same because we are changing only R2. The first row we should write as it is, 2 1, and look at the second row. Second row gets multiplied by 7. So 0 multiplied by 7 is equal to 0, and 1 by 7 multiplied by 7 is equal to 1. This is equal to, again here also on the right hand side, first row remains the same, so we have 1 0 at this position, and on the second row we are having 7 times the second row. So multiply it with 7, this becomes minus 49 by 2. If you multiply by 7, it becomes minus 49 by 2, check it out. and 1 into 7 becomes 7 multiplied by A. So now here we have also attained a 1 successfully at this position. The next element that we should try to make is 0. So 1 should be changed to 0 at this position. What should we do so that this becomes a 0? Think about it. It's easy. It is this row minus that row and put the result in this position. So that operation of choice would be R1 gets changed to R1 minus R2. R1 gets changed to R1 minus R2. So what is R1? Let's write it. R1 is 2 1. R1 is 2 1 and R2 is 0 1. R2 is 0 1. So now we see that R2 is not getting changed. R2 remains the same. So write R2 as it is 0 1. Look at R1. R1 now becomes R1 minus R2. So 2 minus 0 is equal to 2. And then 1 minus 1 becomes 0. Same thing you have to do on the right hand side as well. On the right hand side, first row is 1 0 and the second row is minus 49 by 2 and this is 7. Now we see that the second row does not change here, so keep the second row as it is and only the first row gets changed, and that is R1 minus R2. So R1 minus R2 in this position is 1 minus minus of 49 by 2, that is 1 plus 49 by 2. That would become 1 plus 49 by 2, and that is, if you simplify it, it is 51 by 2. 51 by 2 at this position. And then 0 minus 7 is minus 7. So we have a minus 7 at this position multiplied by A. Okay, now what is the last number? That is, so we have successfully attained a 0 here at this position, we have a 0 at this position, we have a 1 at this position. The last number that should remain is this number. We have to change this 2 into 1. So how can we achieve that? Yes, by dividing the entire first row with the number 2. So the operation of choice is first row gets changed to first row divided by 2. So if we do this operation, entire first row gets divided by 2. So we have 2 divided by 2, 0 divided by 2, 51 by 2 divided by 2, say minus 7 by 2, right? So this will become 2 by 2 is equal to 1, 0 by 2 is 0, minus 51 by 4, 2 2s are 4, and this is minus 7 by 2. So we are seeing that on the left hand side we have identity matrix and on the right hand side we have this matrix, right? So now we know that if two matrices are multiplied and the product is an identity matrix, then these two matrices must be inverses of each other. So inverse of A is this matrix, which is the required answer. So A inverse is equal to 51 by 4 minus 7 by 2 minus 49 by 2 and 7. Try to verify this result at your home. Okay, so this is the answer. Let us solve another question. This one, 2 5 1 3. So this is a matrix, suppose A, and it is asking you to find A inverse, right? So if we are using elementary row operation, that is the first equation that we will write is A is equal to I into A. Putting the value of A in this position, we have 2 5 1 3 is equal to, putting the value of I, we have 1 0 0 1, and then we leave A as it is. Then this left hand side should become then identity matrix of order 2, just like this. So what is the first element that we should try to make 0 is this one. So how can we make this element 0? Yes, by dividing the first row by 2 and then subtracting this row from that row and putting the result in the second row. So the operation of choice would be R2 gets changed to R2 minus R1 by 2. So look at the first row. We have the first row equal to 2 5 and the second row is equal to 1 3. Now first row gets divided by 2, so 2 by 2 is equal to 1, and we have 5 by 2 here. Now we are saying that R1 is not getting changed to R, so place R1 as it is and look at the concentrate on the second row. In the second row we will have R2 minus R1 by 2, so R2 minus R1 by 2 is 1 minus 1 is 0 at this position, and 3 minus 5 by 2 in this position. So 3 minus 5 by 2 is equal to 6 minus 5 by 2, this is 1 by 2, so this is equal to half at this position, right? Similarly on the right hand side we are saying that the first row is 1 0, the second row is 0 1. So after dividing the first row by 2, we have 1 by 2 at this position and 0 by 2 is 0. So now we see that first row is not getting changed, to pick the first row as it is, and in the second row we are having R2 minus R1 by 2. So R2 minus R1 by 2 is 0 minus half is minus half, and 1 minus 0 is 1. Place it here, multiplied by A. So we are seeing that we have successfully attained a 0 at this position. The next number that you should try is this one, 1. So how can we achieve a 1 here? Yes, by multiplying the entire second row with 2. So the operation of choice at this point is R2 becomes 2 times of R2. So that means we have to multiply the entire second row with the number 2. So 0 into 2 becomes 0. Half into 2 becomes 2 to cancel out, becomes 1. So half into 2 equal to 1. Here also minus half into 2 is equal to minus 1, and 1 into 2 becomes 2. So we are seeing that after this operation we are left with this matrix equation, and we are seeing that we are successfully attaining a 1 here. The next element that we should target is this one. We have to make this element as 0. So how can we achieve a 0 here? Think about it. Yes, by multiplying the second row with the number 5 and then subtracting this row from that row and putting the result in the first row, we get a 0 here. So the operation of choice this time would be R1 getting changed to R1 minus 5R2. R1 minus 5R2. Okay, so see, we have R1 is equal to 2 5 and R2 is equal to 0 1 0 1. Then 5 times of R2 would be 0 into 5 is equal to 0, and 1 into 5 becomes 5. So now we see that the first row is getting changed but the second row is not getting changed. So place the second row as it is and look at the first row. First row becomes R1 minus 5R2. R1 minus 5R2 is 2 minus 0 equal to 2. Place it as it is, and 5 minus 5 is 0. So place 0 here. In a similar way, in the right hand side we have R1 is equal to 1 0, and we have R2 is equal to minus 1 2. So R2 is equal to minus 1 2. Then 5 times of R2 would be minus 5 and 10, right? So now we see that R2 is getting changed, sorry, R1 is getting changed but R2 remains the same. So place R2 as it is and concentrate on the first row. First row gets changed to R1 minus 5R2. So R1 minus 5R2 is 1 minus 5 means 1 plus 5, and that is equal to 6. So we have a 6 at this position, and then 0 minus 10 is equal to minus 10. Place it here, multiplied by A. So we see that we have successfully attained a 0 at this position also. The last element that is remaining is 1. So we should make this 2 equal to 1. How can we do that? How can we change the number 2 to 1? Yes, by dividing this entire row with the number 2. So if the operation of choice would be now that R1 changes to R1 by 2. So if we do this operation, we are left with, we will have now The second row remains same, so we will write second row as it is. And look at the first row. First row gets divided by 2. So 2 divided by 2 is equal to 1. 0 divided by 2 is 0. And on the same right hand side, we should also divide by 2. Second row remains the same. Look at the first row. 6 divided by 2 is equal to 3. And minus 10 divided by 2 is minus 5 into A. Now look at this equation. This is becoming identity matrix after multiplication of these two matrices. And by definition of inverts of a matrix, we know that if two square matrices get multiplied and the product is identity matrix, then these two matrices must be inverts of each other. In other words, inverse of A is this matrix. So this matrix is nothing but A inverse, and I say that A inverse is equal to 3 minus 5 minus 1 2, and that is your answer. Okay, so now we have solved several examples. Let us solve another example. This time it will be a 3 by 3 square matrix. Let us look at an example here. Let us say we have a matrix A is equal to 0 1 2 1 2 3 and 3 1 1, and it is asking you to find A inverse. Okay, so try to solve it using row operations. So as we already know, for row operations, the first equation that we should write is A is equal to I into A, right? So this is a 3 by 3 matrix, this time 3 by 3 square matrix. So put the value of A here. We have 0 1 2 1 2 3 and 3 1 1. Putting the value of I 1 0 0 0 1 0 0 0 1. This is a 3 by 3 identity matrix, and we put the value of A as it is. Okay, now our aim is to make this side equal to identity matrix. So our aim is to achieve this matrix here, 1 0 0 0 1 0 and 0 0 1. So let us try to make this matrix here. So what should we do? The first element that we should target is this one. So target this matrix, this element here. How can we make it a 0? Think about it. How can we make this 3 as 0 at this position? Think about it for a second. Yes, we should multiply the second row with the number 3, and then subtract the third row from the second row and putting the result in the third row. So the operation of choice at this position should be R3 gets changed to R3 minus 3 times R2. So R3 becomes R3 minus 3 times of R2. So try to do it. Look at the first row, it is not getting changed. Only the second and third rows getting changed. So let us write the second row. Second row is 1 2 3. 1 2 3, and the third row is 3 1 1. Third row is 3 1 1. Right. Now 3 times R2. So 3 times R2 will be 1 into 3 is equal to 3. 3 2s are 6. 3 3s are 9. Right. Now first row is not getting changed. So place the first row as it is. Now second row is also not getting changed, because since we are using only the third row transformation, so second row remains same. And look at the third row. Concentrate on the third row. We have third row is equal to R3 minus 3 R2. So 3 minus 3 is 0. Then 1 minus 6 is minus 5. And then 1 minus 9 is minus 8. This should be equal to a similar fashion. On the right hand side, we will have the second row equal to 0 1 0. And the third row is 0 0 1. So 3 times R2 will be 0 into 3 is equal to 0. 1 into 3 is equal to 3. And 0 into 3 equal to 0. First row is not getting changed. to place the first row as it is. Second row is also not getting changed, so place the second row as it is. Only the third row is changing, and third row is changing to R3 minus 3 R2. So 0 minus 0 is 0, 0 minus 3 is minus 3, and 1 minus 0 is 1, and we have A here. So now we see that we have successfully attained a 0 at this position. The next 0 that we should target is this minus 5. So change this minus 5 to 0. How can we do that? Think about it for a second. How can we achieve a 0 at this position? Look at the first row, concentrate on the first row and the third row. Can we do any operation so that this becomes 0 at this position? Can we do anything? Yes. What can we do? Tell me. We can multiply the first row with the number 5 and then add these two rows. So R3 will be changed to R3 plus 5 times R1. If we do this, that means first row gets multiplied by 5 and then add both the rows and then place the result at this position. So we see that the first row is 0, 1, 2, 0, 1, 2, and the third row is 0, minus 5, minus 8. Third row is 0, minus 5, minus 8. Now 5 times R1 will be equal to 0 into 5 is equal to 0, 1 into 5 is equal to 5, and 5 into 2 is equal to 10. So now we see that, let me rub it out. We see that in the first row is not getting changed, so place the first row as it is, 0, 1, 2. Second row is also not getting changed, so place the second row as it is. In a similar way, look at the third row now. Third row is getting changed this time, and that is R3 plus 5 R1. So R3 plus 5 R1 is 0 plus 0 is 0. Minus 5 plus 5 is 0. And minus 8 plus 10 is equal to 2. Right. And this is equal to, on the right hand side again, first row remains same. Second row also remains same. And look at the third row. So on the right hand side, the first row is 1 0 0, 1 0 0. Third row is 0 minus 3 1, and 5 times of R1 is 1 into 5 is equal to 5, and 0 into 5 is 0, 0 into 5 is 0. So in the third row we have R3 plus 5 R1. So 0 plus 5 is 5. Then minus 3 plus 0 is minus 3. Then 1 plus 0 is 1. So we see that we have successfully attained a 0 at this position as well. The next number that you should target is 1. So looking at this 1, we have 2 here. So how to change this 2 into 1? Yes, by dividing the entire third row with the number 2. So we should use this operation. Third row becomes third row divided by 2. So after we divide by 2, what do we get? 0 by 2 is 0, 0 by 2 is 0, 2 by 2 is equal to 1. And look at this position here. What do we have? 5 by 2, minus 3 by 2, and 1 by 2. Okay, so after this operation, we are left with this matrix equation. So we see that we have successfully attained a 1 at this location. Now take a good look and see what we should attain in the next position. The next element that we should target is 0. So how can we make a 0 at this location? Think about it for a second. Remember elementary row column operation. What was the first operation? Can we interchange two rows? So if we interchange the first row with the second row, so we are easily getting a 0 here. That means if we make the first row appear here and the second row appear there, then we are easily getting a 0 at this location, just as it is. Okay. So if we are changing the first row with the second row, remember this sign, double arrow, that means interchanging. So first row reaches the second position and the second row reaches the first position. So in the first row we have 0 1 2, 0 1 2 comes here and 1 2 3 gets there. So we have just changed the rows. Similarly, you have to change the row here also. It is changed now. So R1 becomes R2 and R2 becomes R1. On the right hand side also R1 becomes R2, R2 becomes R1. Now we see that we have successfully attained a 0 at this location also. Now we have a 1 here, so no need to do anything here. But we have a 2 at this position. So you have to change it to 0. So the next element that we should target is 0. So how can we make a 0 at this location? Think about it for a second. How can we achieve a 0 at this position? Think about it and tell me, what should we do? I am giving you 2 seconds to think about it. Yes, we should do that. We have to multiply the third row with the number 2 and then subtract the second row from the third row and then putting the result in the second row. So the operation of our choice should be second row gets changed to second row minus 2 times the third row. So writing the second row here, we have second row is equal to 0 1 2, 0 1 2 and third row is 0 0 1, 1. Now 2 times the third row, 0 into 2 is 0, 0 into 2 is 0, 1 into 2 is 2. Now we see that first row, is the first row changing? No. Is the third row changing? No. Only the second row is getting changed. So what is the second row now? R2 minus 2R3. So R2 minus 2R3 is 0 minus 0 is 0. We are not going to change. 1 minus 0 is 1. We have 1 here. And then 2 minus 2 is equal to 0. Right? And on the right hand side also, first row is not changing, so it is remaining the same. In a similar way, third row is also not changing, it is remaining the same. And in the second row we will have R2 minus 2R3. So in this matrix we have R2 is equal to 1 0 0 and R3 is equal to 5 by 2 minus 3 by 2 half. So 2 times R3 would be 5 by 2 into 2. So 2 cancel out, we have 5. Minus 3 by 2 into 2, 2 cancel out, we have 3. 1 by 2 into 2, 2 cancel out, we have 1 only. So that this is 2 times R3. And we have to place the result on the second row. And second row becomes R2 minus 2R3. So R2 minus 2R3 is 1 minus 5 is equal to minus 4. Then 0 minus minus 3 becomes 0 plus 3, which is equal to 3. And then finally we have 0 minus 1. So 0 minus 1 is minus 1. Okay. Now we see that we have successfully attained a 0 at this location, just like it is. Now tell me, what should we do next so that we have this matrix? Think about it for a second. What should we do next? Yes, the next that we should try is to make this element as 0. So how can we make this element as 0? Think about it. Tell me, I am giving you 3 seconds to think about it. How to make this 3 0 at this location? Think about it for a second. Yes, we should multiply the third row with the number 3 and then subtracting this entire row from the third row and placing the result in the first row. So the operation of our choice should be like that: first row is getting changed to first row minus 3 times the third row. First row minus 3 times the third row. So let us see what is the first row. First row is 1 2 3, 1 2 3, and look at the third row. Third row is 0 0 1. So third row is 0 0 1, and 3 times the third row. 3 times the third row is 0 into 3 is 0, 0 into 3 is 0, 1 into 3 is 3. So now we see that second row is not getting changed, only the first row is getting changed. So second and third rows remain same. So change the first row and the first row becomes R1 minus 3R3 So 1 minus 0 is equal to 1, no need to change. 2 minus 0 is equal to 2, no need to change. 3 minus 3 is equal to 0. So this becomes 0. In a similar fashion, look at the matrix on the right hand side. We have R1 is equal to 0, 1, 0. And we have R3 is equal to 5 by 2 minus 3 by 2 and then 1 by 2. So 3 times the third row is equal to 5 3s are 15, 15 by 2. 3 into minus 3 by 2 is minus 9 by 2, and 3 into half is equal to 3 by 2, right? So now second and third rows remain same, only the first row is changing, and that would be R1 minus 3 R3. So what is R1 minus 3 R3? 0 minus 15 by 2 is minus 15 by 2. Next we have 1 minus 9 by 2, that means 1 plus 9 by 2. So we have 1 plus 9 by 2, this is equal to 11 by 2. So we have 11 by 2 here, and then finally we have 0 minus 3 by 2, that is minus 3 by 2 at this location. Okay, so now we see that we successfully attain a 0 at this location. The last number that we should try is this one. The only last number that is remaining is 0, because 1 is already here. So how to make a 0 at this position? At this position we have to try to make it a 0. Think about it, what should we do next? I am giving you 3 seconds to think about it. Okay, what should we do is that we should multiply the second row with the number 2 and then subtract the first row from the second row and then putting the result here. So the operation of our choice should be first row getting changed to first row minus 2 times the second row. Okay, so first row is 1 2 0 and second row is 0 1 0. Now 2 times the second row would be 0 into 2 0, 1 into 2 is 2 and 0 into 2 is 0. So look at the first row, 1 2 0, we have R1 minus 2 R2. So 1 minus 0 is equal to 1, we no need to change. 2 minus 2 is 0, so this becomes a 0, and then 0 minus 0 is 0. And on the right hand side we have R1 is equal to minus 15 by 2, then we have 11 by 2 and then minus 3 by 2, and R2 is minus 4, 3, minus 1. So 2 times the second row, minus 8, 6 and minus 2, right? So now first row is getting changed to R1 minus 2 R2. So this minus that, here is minus 15 by 2 minus of minus 8, that means minus 15 by 2 plus 8, or 8 minus 15 by 2, and this is equal to 16 minus 15, that is half. So we have a half at this position, and on the next position R1 minus 2 R2 is 11 by 2 minus 6. So what is 11 by 2 minus 6? This is 11 minus 12 by 2, and that is minus half, right? So we have a minus half at this position, and on the third position we have minus 3 by 2 minus of minus 3 by 2, that means it is minus 3 by 2 plus 2, that means it is plus 2 minus 3 by 2. So we have plus 2 minus 3 by 2, this is equal to 1 by 2. So we are having a 1 by 2 at this location. So we see that this left hand side has become a identity matrix I, and on the right hand side we have two matrices getting multiplied, one is A, other one is this matrix. And we know by the theory of inversion of a matrix that if two square matrices get multiplied and the product becomes I, then these two matrices must be inverse of each other. In other words, this matrix is inverse of A. So this matrix is A inverse. So finally we see that A inverse is half minus half, half minus 4, 3 minus 1, 5 by 2 minus 3 by 2 and half. And this is your answer. Try to practice this at home as many times as you like and try to reach this result. Okay, now it must be clear to you how to find inverse of matrix using row operations. The same thing you can do with column operations as well. There is no harm in it. So try to use column operations as well. Okay. Now just in the last class I told you that not every square matrix is invertible. So write a statement here. Not all square matrices are invertible. A very important statement. It states that not every square matrix is invertible. That means there is no guarantee that every square matrix will have an inverse. Some of the matrices will have inverse, some matrices will not have an inverse. Let us look at a very specific example and we will see that this matrix will not have an inverse. So let us write a question. Let us say we have a matrix A is equal to 10 minus 2 and minus 5 1. Let us suppose we have a matrix like this. Okay, and try to find A inverse. This is just a question that we have solved up till now. It is a very similar question. Try to find A inverse. So using row operations, as we already know, the first equation that we write is A is equal to I into A. Putting the value of A, we have 10 minus 2 minus 5 1. Putting the value of I, it is 1001 into A. Okay, we should make this right hand side equal to identity matrix 1001. The first element that we should target is 0. So try to make a 0 at this position. So how can we make a 0 at this position? Think about it for a second. How can we make it a 0? How can we make it a 0? Yes, if we divide the first row by 2 and then add the first row with the second row and putting the result in the second row. So our element operation of choice will be second row gets changed to second row plus first row divided by 2. So our first row is 10 minus 2. First row is 10 minus 2 and the second row is minus 5 1. Okay, then R1 by 2 is equal to 10 by 2 is 5, minus 2 by 2 is equal to minus 1, right? Then second row gets changed. First row is not changing, only the second row is changing, and that is changing to R2 plus R1 by 2. So what is R2 plus R1 by 2? Minus 5 plus 5 is 0. So put a 0 here. Then we have 1 plus minus 1. What is 1 plus minus 1? Again another 0 at this position. Similarly on the right hand side we are having R1 equal to 1 0 and on the second row we have 0 1. So R1 by 2 will be equal to half 0. 0 by 2 is 0. So the first row is not changing, second row is changing, and that is changing to R2 plus R1 by 2. So 0 plus half is half. So place a half here, and then 1 plus 0 is 1. No need to change, it is 1 there already. So now we see that here we are achieving a 0 0. There is no way that we can achieve a 1 at this position. Can we make it a 1 by any means? Can we make a 1 here? If we try to make 1, how can you make it? Think about it. Well, you might say that let us divide the second row by 2, so we will achieve a minus 1 here. One might tell that yes sir, we can make a 1 at this position by doing R1, R2 getting changed to R2 plus, sorry, one might achieve a 1 here by dividing the first row is 0 minus 2, divide by 2, it becomes 5 minus 1 if we divide by 2, and then subtracting this row from that row. So if we subtract this row from that row, we will have what? After subtraction we will have 1 at this position, but we will also have minus 5 at this position. So we see that we do achieve a 1 here, no problem, but this is not getting 0 again. This is becoming minus 5 this time. So whatever we have done earlier, it is not getting done in this step. That means it is changing back to minus 5. So if we try to make it a 0, we get a 0, but if we try to make it a 1, it is not possible. So we see that this becomes 0, 0, and it is no longer possible to make this matrix at this location. So this simply means that this matrix is not invertible. Since we cannot make this matrix an identity matrix, we cannot make it. So that means that this matrix A is not invertible. That means whatever you do, whatever operation you choose, you cannot make this matrix multiplied by a matrix at this location equal to I. So if you cannot do this, that means this matrix is not invertible. That means its inverse does not exist. Inverse of this given matrix does not exist. So A inverse does not exist. So it is clear to you that we cannot make we cannot find out the A inverse or because A inverse does not exist. There is no matrix such as an A inverse that is existing for the given matrix. We cannot make this left hand side as identity matrix by any row or any column operation. Whatever operation you do, you will never make it a identity matrix because the entire row becomes a 0. How can we make it? So let me tell you another trick. Here is a trick that you can use to verify instantly whether any matrix is invertible or not. What you do for a 2 by 2 matrix, you will have to find the determinant. Now you may not be aware of determinants because determinants is your next chapter. Determinants is in your next chapter. But determinant simply means that this multiplied this minus this. So what is 10 into 1 is 10 minus 5 into minus 2. If this is equal to 0, then this matrix is not invertible. In this case, we see that 10 into 1 is 10 and minus 5 into minus 2. So minus 5 into minus 2 minus plus 5 into 2 is 10. So we see that 10 minus 10 is becoming 0. So if the determinant of this matrix becomes 0, if for any matrix, if determinant is 0, then that matrix does not have an inverse. In our case, we see that determinant is 0. This is just a trick, by the way, I am telling you just a trick. So determinant is 0, that means this matrix does not have an inverse. But in your book, for matrices, the correct procedure is to follow this step. We see that we cannot make an inverse here. We cannot make an identity matrix here. So that means that this matrix does not have an inverse. Okay. So this is an example just to show you this statement that not all square matrices are invertible. It is not possible that I give you every square matrix and every square matrix should have an inverse. No, it is not always possible. Some of the matrices do not have an inverse. So now it must be clear to you that every matrix does not have an inverse. Keep that in mind, and this is the trick. You should also keep this in mind to check it instantly whether a matrix has an inverse or not. Okay. Let us study two important theorems based on inverts of a matrix. We have a theorem number 1 based on inverts. These are just theorems. So you are advised to keep these theorems in mind while solving problems. First theorem is inverse of a matrix, inverse of a square matrix if it exists is unique. So this is your first theorem. It states that if a square matrix have an inverse, then that inverse will be unique. That means, for example, if I say A is a matrix 1, 2, 3, 4, and suppose, for example, A inverse is some matrix this, then this matrix have only one inverse possible. There is no another, that means you cannot make another matrix that will be an inverse of this matrix. So every matrix have only one inverse possible, that means it is unique. So this matrix, it is an identification then this matrix is an inverse of this matrix, or this matrix is an inverse of that matrix. So it is an identification that every matrix will have a very particular inverse, and every inverse will have a very particular matrix. So that means this is unique. Okay, so you have to keep this in mind. For example, you have a unique fingerprint, right? You have a unique fingerprint. Your fingerprint will not match with another person's fingerprint. So in a similar way, this matrix will have its own inverse. It will not be the same as another matrix. You cannot say there that I write another matrix B, and suppose this is another matrix like this, and this has the same inverse. No, it is not possible. This matrix will have only one inverse, and that is this matrix. It cannot be inverse of any other matrix. Whatever matrix you choose, you cannot have any other matrix that will give, after inverting that you will get that. No, it will have only one matrix that will be inverse of each other. Okay, just like your fingerprint. So inverse of a square matrix, if it is existing, then it will be unique. That means it will be only one in number. So this is your first theorem, and in your second theorem you have, second theorem is, if you are multiplying two matrices and you take the product, and after taking the product, if you take the inverse, then this will be equal to B inverse multiplied by A inverse. That means just this matrix will change their position. B will come in the first place, A will come in the second place, and inverse will be present on the both matrices. So if you want to place this -1 on both these, that means if you place -1 on both of these matrices, then you should write in this opposite fashion. B becomes the first matrix, A becomes the second matrix, and then put inverse on individual matrices. So this is the rule, or this is the second theorem. It is also very easy to prove. You can write A into B, or you can simply write it as AB. Okay, it does not matter, it is the same thing. So let's try to prove it. So let us prove this theorem. So we can say that for any matrix, we already know that if you multiply a matrix with its inverse, we get what? Identity matrix. We already know that. We have been solving so many problems, and we are seeing that any matrix, when multiplied by another matrix, it becomes identity matrix. Right? So similarly, let us say we have a matrix AB. Let us say AB is the matrix. That means product of A and B, it is a new matrix, right? So let us say this is the new matrix, and you multiply this matrix with its inverse. So what will happen? Remember, what did I write here? Any matrix multiplied by its inverse is equal to identity matrix, right? Now let us try to multiply A inverse on both sides. So multiply A inverse on left hand side and A inverse on the right hand side. So after multiplying A inverse, this becomes like this. Okay, and we already know A inverse into identity matrix is what? A inverse, because any matrix, A inverse is still a matrix, right? So any matrix when multiplied with an identity matrix, it becomes the same matrix. We already know that. Okay, now removing the bracket here, we see that we have A inverse into A. And tell me again, any matrix multiplied by the same matrix, that means any matrix multiplied by its inverse is equal to identity matrix, right? So we can say that this A inverse into A is equal to another identity matrix, I. Is it not right? Yes. So this will become identity matrix. So we are seeing that identity matrix into B into AB inverse is equal to A inverse. Now recall again, identity matrix into this entire matrix is again this entire matrix, because whether you multiply it by I or not, it does not matter. So if you write I here, or if you do not write I, it does not matter. So you are left with B into AB inverse is equal to A inverse. Now you do one thing, you multiply by B inverse this time. So now let us try to multiply B inverse on both sides. That means B inverse will come in the first position, right? Now again the same situation. Again we are seeing that B inverse is multiplied by B. So we see that any matrix multiplied by the same inverse of that matrix is again I. So I can change this to I. Okay. So now we have I into AB inverse, and we already know if you multiply by I, it is the same matrix. So writing I or not writing I does not matter. So we are seeing that AB inverse is equal to B inverse into A inverse, and this is what we have seen in this theorem number 2. So here we have finally proved that theorem number 2, and that is AB whole inverse is equal to B inverse into A inverse. So this is a very important theorem. You try to keep this theorem in your mind and also try to practice this proof at your home. Okay, so I hope that you have understood matrices properly and try to solve as many problems as possible. I am giving you some practice problems based on inverts of a matrix. Try to solve all of this at your home, and hopefully in the next class we will move to the next chapter. So I am giving you homework. These are all homework. Find A inverse if A is equal to number 1 3152. Another question 4534. Another question 31027. Try to solve this at your home. And let us give you another question 1 3 minus 2 minus 3 0 minus 5 250. Okay, so these are the 4 questions that I am leaving you as a homework, and hopefully in the next class we will meet with a new chapter. So thank you very much for listening, and try to practice as many problems as you like. You can also make matrices by yourself and try to find their inverse. Try to memorize this theorem. Both the theorems are important, especially the second theorem is important, that AB whole inverse is equal to B inverse into A inverse. And also try to remember the elementary row and column operations. Also it is also important to remember these steps like A is equal to I into A for using row operations, and for column operations if you choose, then you can use this equation. So that's it for today, and hopefully we will meet on the next class with a new chapter. So you are advised to go through all problems in this chapter from any book you like and practice all the problems, and if you have any queries then you can leave a comment in the comment section below, and hopefully we'll meet in the next class. So thank you very much.